Swayam Prabha. Digital India. Educated India.
The title of my talk is Reimagining System Science in the Era of Artificial Intelligence and Machine Learning. This is a perspective talk with a simple introduction of AI and machine learning techniques that help in the process of analyzing and discovering information from data from operating processes, with examples of applications in agriculture, healthcare, mining, and material science. This is not a scholarly talk. There will be few references, hardly any equations. It is a perspective talk. It is geared towards what the future holds and the areas and projects to pursue that hold a lot of promise. The main focus is to show how data analytics and information extraction is being applied to a wide spectrum of fields. Let me start by defining the term analytics. We shall use this term time and again. And so the definition of analytics is, it is the discovery and purposeful utilization and communication of meaningful information and patterns in your data. With the growing interest in AI, the term analytics is very widely used. And it is the availability of massive volumes of data, powerful algorithms, and fast computers that have enabled us to do analytics. There is increasing and growing interest in AI from industry and governments because of comments such as the following quote: "Information is the oil for the 21st century, and analytics is the combustion engine." End of quote. This comes from Gartner Research. Gartner is a very reputable technology consulting and advisory firm in the US. Another interesting quote on AI is, quote, "AI is the new electricity." End of quote. This comes from Andrew Ng, who is the director of Stanford's AI lab. What it means is, the age of artificial intelligence can be related to the discovery of electricity for allowing inexhaustible applications into all walks of life. AI might be the single largest technology revolution of our times. And we are already living in an AI-led era, be it Amazon's Alexa or Apple's Siri or the Google Assistant. Our smartphones now are all equipped with personal assistant powered by AI with nearly 90% accuracy and dependability. What is propelling the drive to AI and machine learning is the massive volumes of data. This brings me to the second quote, which goes on as follows: "There are 5 exabytes of information created between the dawn of civilization up to 2003. And that much information is now created every 2 days." End of quote. 1 exabyte is 1 billion gigabytes. Imagine the massive volumes of data that we are archiving and collecting. This comes from Eric Schmidt, who is the past executive chair at Google. So looking ahead, there are certainly paradigm shifts underway, and it is faster networks, computers, and algorithms that is propelling a drive for better productivity and performance. And therefore the world is changing at an unprecedented speed. AI, machine learning, and deep learning are making it possible to have intelligent conversations with machines. However, be aware the outputs aren't always accurate or appropriate. ChatGPT seems to have trouble counting or solving even simple basic algebraic problems, or indeed overcoming the sexist and racist bias that lurks in the undercurrents of the internet and society more broadly. So you have to be careful on how you use ChatGPT and such conversational algorithms. AI is also making possible accelerated drug discoveries with molecular simulation, plus many other widespread applications. Easy access to AI and machine learning means that powerful algorithms will be available easily, and this will lead to democratization of exploration and help the next generation of engineers overcome challenges such as the following. With a world population of over 8 billion, we will need to ensure water, food, and energy security for everyone. We will need to improve efficiency and productivity, keeping in mind the sustainability, environmental, social governance, and such issues in mind. There will be long-term societal benefits through improved health care. For example, in 2020, Regina Barzilay and MIT professor Jim Collins announced the discovery through deep learning of halicin, the first new antibiotic compound in 30 years. The researchers used AI to search through millions of candidate chemical compounds by first training them on chemical structures of known antibiotics and how well or how not they'd worked against the bugs. During this training, the model was able to establish links between chemical structures and their success rate at damaging bacteria. The AI algorithms then spat out a short list of potential candidates. It will still take many years to take the candidate drug from the lab to clinical trials, but AI has significantly accelerated the trial part of this process. Increasing use of sensors everywhere and new Industry 4.0 standards with fast data access will mean more information to extract for decision support. AI and machine learning will also enable better monitoring of process systems, resulting in improved safety. For example, the Boeing 73 MAX 8 disaster, which led to a loss of almost 300 lives due to a faulty sensor and its inability to disable the automated flight system, will be a thing of the past. Here is the outline of my talk. I'm going to give you a very quick overview of AI and machine learning, and then we will go on to explore applications in water and precision irrigation systems, battery development, computational pathology, quantification of steel microstructures, and finish with a short talk on data ingestion and a simple case study. Generative pre-trained transformers, commonly known as GPT, are a family of neural network models that use the transformer architecture, which is the key advancement in powering generative AI applications such as ChatGPT. In 2017, Google authors published a paper called "Attention is All You Need." This led to a transformer model that learns context and therefore the meaning by tracking relationships in sequential data, such as the word in the following sentence. And let me say a sentence. The pizza was baked in the oven. It tasted very good. I repeat, the pizza was baked in the oven. It tasted very good. So from a context point of view, the question is, what tasted very good? Was it the pizza or was it the oven? We know it was the pizza, but if you ask that question to an NLP algorithm, it has to sort the context out, and the transformer architecture allows it to do so. So transformer models apply an evolving set of mathematical techniques called attention or self-attention to detect subtle ways even on distant data elements in a series and how they influence and depend on each other. And these ideas are being applied to text, speech, and image data as well. And all of this data is then used for training purposes to develop a foundation model which can then be used to attend to different tasks such as questions and answering, information extraction, image captioning, object recognition, instruction following, and so on and so forth. Okay, so to try and summarize the main parts of my talk, I looked for an image that would serve as a metaphor for the massive volumes, the torrent of data that we find ourselves engaged in. Data comes in many shapes and colors, meaning many different formats and data types. And so in dealing with analytics, one has to deal with different types of data set, for example, spectroscopic data, or data from three-dimensional spatio-temporal systems, such as used by people who do mining, or data sets from pixelated correlation maps, or data or image data, or vibration data from a rotating machinery, or process flowsheet data, and business data, and now, of course, you have text from natural language processing algorithms and LLMs, large language models. The important message that I wish to convey through this slide is that unless you're armed with the right flotation aids, meaning right analytic tools, you can easily sink in the sea of data. The terms big data and analytics that I refer to in this slide, in a very simplistic way, relates to analyzing large amounts of data using machine learning methods. To clarify this terminology, let's see how AI and machine learning are defined. AI is composed of many different fields or areas, and I only show you the machine learning and the DL or the deep learning parts that comprise AI. AI is software algorithms that can reason, infer, and think like humans, or the practice of getting machines to mimic human intelligence to perform tasks. Machine learning, on the other hand, is the science of getting computers to learn without being explicitly programmed. You can do this via unsupervised, supervised, or reinforcement learning algorithms. The argument is that this is what is going to lead to the democratization of exploration. One need not understand the coding part of machine learning algorithms, and anybody can have access to a lot of the codes that will allow you to extract information from data. Deep learning is a subset of machine learning in which multi-layered neural networks learn from vast amounts of data. Neurons are part of a mathematical model that mimics how a neuron in a brain works. Many different fields comprise artificial intelligence. Our focus is mainly on machine learning, but other areas such as knowledge and inferencing, here, natural language processing, machine learning, and learning probabilities for risk analysis that people from the insurance industry use. These are also important. Much media attention has recently been given to generative AI algorithms such as ChatGPT and Google's Bard. They all rely on natural language processing and large language models. Interest from AI from industry, government, and academia is very high because of powerful computers, explosion of data, and efficient algorithms. And the explosion of data is because of the Internet of Things. The total installed base of IoT connected devices is projected to amount to 75 billion worldwide by 2025. That's a five-fold increase over 10 years. So look here, this was the number of installed base in 2015, and it is now over 75 billion connected devices. The IoT enabled by the already ubiquitous Internet technology is the next major step in delivering Internet's promise of making the world a connected place. There is also large increases anticipated in IoT connected devices because of 5G and their fast wireless networks. So this brings us to massive volumes of data. There was an article in the 2019 issue of IEEE Spectrum with the title Data World, Racing Towards Iota. And the question raised therein was, how much data should we be storing and for how long? And they're talking of iota devices. So remember, 1 exabyte is a billion gigabytes, and in fact 1 iota is a million exabytes. Imagine the amount of data that we have to store. 1 iota is 10 to the power 24 bytes. Generative pre-trained transformers, commonly known as GPT, are a family of neural network models that uses the transformer architecture, which is a key advancement in AI applications such as ChatGPT. GPT-3 was trained on 45 terabytes of text data. That's 45,000 gigabytes of text data. That's about 1 million feet of bookshelf space, or a quarter of the entire Library of Congress. And this came at an estimated cost of several $million, almost $100 million. ChatGPT required many, many months to train, and even many more months for the models to be validated and monitored. The large language models based on neural networks required trillions of parameters. So human intelligence is complex, and the transformer architecture doesn't always get it right. So remember, information is highly contextual. So even the transformer architecture doesn't always get it right. Expert or domain knowledge is tacit, it's hidden, it's implicit, and not easy to capture or automate. AI systems based on large language models need training on massive volumes of data. Here is the timeline of how generative AI has been thrust upon the world community. It is less than 15 months since ChatGPT 3.45 was introduced. This was in November 30 in 2022, less than 15 months ago. Since then, many other software vendors have entered the market with specialized large language models in very niche markets. Here are some examples. Google's MedPalm was trained for clinical knowledge. And then, if I go to the next slide, Bloomberg announced an LLM trained on financial data. So everybody is working on LLMs for very niche markets. The important highlight to note is that ChatGPT gained a record number of users, almost over 100 million users in less than 2 months since it was announced. The people who developed deep learning methods using convolution neural networks are Jeff Hinton from the University of Toronto in the middle here, Yoshua Bengio on the left from École Polytechnique in Montreal, Canada, and Yann LeCun, who is now with Meta. Yann LeCun is on the right here. Both Hinton and Bengio have discussed and commented widely on the potential promise and perils of AI. AI will help in discovering wonder drugs, will help in accelerate the discovery of advanced materials for batteries, but can also be used to create and spread misinformation, can create and spread propaganda that can create wars and social unrest, and even help build destructive weapons. So you have to use these algorithms very wisely. We need to be mindful, therefore, on how AI is used, and governments and institutions have to have the legislative rules and the machinery to put checks and balances on the development and use of these tools. Both Yoshua Ben-Gio, Jeff Hinton, and Jan LeCun are CFAR fellows. CFAR stands for Canadian Institute for Advanced Research, and they were jointly awarded the prestigious AM Turing Award for the development of deep learning. This award is regarded as the equivalent of a Nobel Prize in computing. Let's look at machine learning in a very simplistic way. Machine learning involves unsupervised learning or supervised learning. By unsupervised learning, we mean find hidden patterns and information in your data when the data is not labeled. The cause and effect variables are unknown to us, or the input and output variables are not labeled. On the other hand, supervised learning involves working with data where we do have the cause and effect labels or the input and output labels, and you're required to train models for using this data. The important thing to remember is no matter which type of learning you do, informative data is the key. So machine learning with unsupervised learning essentially involves clustering. On the other hand, when you work with supervised learning, you're interested in classification of the data or building models using regression methods. It's a very simplistic way of explaining machine learning. So many methods and techniques are available for supervised and unsupervised learning. The method that many of us may be familiar with include recursive or online model building, recursive least squares, support vector regression and ensemble methods, probabilistic clustering methods, and so on. So clustering will involve methods such as hierarchical clustering, probabilistic k-means clustering. Regression, on the other hand, will involve linear regression methods such as least squares or support vector regression, and so on. Classification, and both regression can use neural network models, and classification can also use neural network models. Now remember, support vector machines is a classifier-derived algorithm from statistical learning theory. It was proposed by Vapnik and Chevronenkis in 1963. That's over 60 years ago. It is now part of a machine learning algorithm. Least squares was conceived by Gauss and Legendre more than 200 years ago, and this is now regarded as a machine learning method. So many of the techniques and methods that have been developed by members of the control community at large, these are now being bundled as AI machine learning algorithms. So a successful analytic project needs building blocks, and those building blocks require good informatics infrastructure, good hardware, software, and particularly teamwork. The teamwork includes co-creation teams with multidisciplinary skill sets for end-to-end model building, and finally deployment and maintenance of models. It turns out that 60% of the models developed in such projects are never actually operationalized. And the reason is lack of tools to enable and facilitate operationalization, meaning validation, adjustment of models to ensure relevancy over time as business and process objectives change, and all of this requires ongoing maintenance and management of models across organization. So the tasks in a well-integrated analytics platform require data ingestion, data preparation, data quality checks. I cannot emphasize these points enough. I cannot emphasize these points enough. Data ingestion, data preparation, quality checks are of paramount importance. In fact, over 70%, sometimes as much as 80% of the effort in an analytics project is in getting the right kind of data, in having the right data set to work with. This is followed by interactive exploration and visualization, feature engineering, which requires selection of important variables and omission of unimportant variables. That leads then to advanced modeling, and finally testing and deployment, also known as model operationalization, and continuing maintenance. Maintenance is an important part. One cannot walk away from these models. Okay. Artificial neural networks are used primarily in deep learning methods. So deep learning methods rely on neural network models with many, many layers. A simple neural network model is an emulation of a biological neuron. Specifically, in an artificial neural network, we do the sum of products of the input. Here are the inputs, multiplied by weights, and then we sum these inputs multiplied by the weights and pass it through an activation function to get an output. So in artificial neural networks, we do the sum of the products of the inputs and their corresponding weights and apply an activation function to get the output for that layer and feed this output to the next layer. Deep learning is essentially artificial neural networks with more than 3 hidden layers. Here is an example of a deep learning model with many layers. So deep learning is artificial neural networks with more than 3 hidden layers. Deep learning is also known as representation learning, and in a sense, with many hidden layers, it replaces the need for feature engineering. You don't need to decide which layers or inputs are important, which inputs are not important. Subsequent layers build increasingly sophisticated representation of data. The input is presented at the next visible layer, so named because it contains the variables that we are able to observe. So the first layer is the color pixel layer. The second layer is the edges. As per the image processing algorithm, the second hidden layer looks for corners and contours. The third hidden layer looks for object parts, and in that way it determines whether the image that we are looking at is an object or a person or an animal. So these series of hidden layers extract increasingly abstract features from the image. And these layers are called hidden because their values are not given in the data. Instead, the model must determine which concepts are useful for explaining the relationship in the observed data. Interest in deep learning using many hid layers was propelled significantly after it was able to reduce the error rate on a benchmark data set below 5%. So look here, in 2010, the error rates were as high as 30%, and use of deep learning algorithms with convolution neural nets led in 2015 with many hidden layers led to error rates which were below 5%. In fact, 5% is the error rate for humans as well. So getting error rates below 5% was considered a landmark discovery. And this is what led to the rapid use of deep learning methods with many layers, deep learning and convolution neural network methods with many layers. The performance of simple machine learning algorithm depends heavily on how we represent data. Each piece of information included in the data set and how we represent that data is known as a feature or a variable. Many AI tasks can be solved by designing the right set of features to extract for the task and providing these features to a simple machine learning algorithm. For many tasks, it is not easy to know which features should we be using. And it turns out deep learning and convolution neural networks do help in that respect. Let's look at an example on why representation matters. The basic idea in clustering, classification, and modeling is to be able to predict outputs. And when we're analyzing data, we want to first ask, can we differentiate and understand the data easily? Can the classification or the clustering on this data be done linearly? Let's look at this example. I show you here a bivariate data set using x1 and x2. If you plot the data for x1 and x2, and they show up as shown here in 3 separate clusters, as shown by the yellow or orange group of data, blue cluster, and green cluster. Well, it turns out in this case, this bivariate data set can be easily classified or differentiated into 3 distinct clusters or classes. On the other hand, if I show you another data set consisting of blue circles and green triangles, we are not able to linearly separate, differentiate, or classify this data set. So this example serves to illustrate that how we choose to represent data is very important. Let's look at the next slide. The question is, can we select a different coordinate system to represent our data? Here is the Cartesian coordinate system that we are using to represent our data. instead of using the Cartesian coordinate, what we can do, we can measure the distance of each point from the center, and that would become the radius, and subsequent points we will measure the angle. So we can represent the data in a polar coordinate system consisting of the angle and the radius. So here is that plot. Here is the angle, here is the radius, and now in this new polar coordinate system, it turns out we can linearly classify or separate the blue dots from the green triangles. It turns out this is exactly the representation that we will use in an agriculture application that I will shortly share with you. Okay, we've completed the overview of AI and machine learning methods, and now we are going to be looking at examples of applications of these ideas in precision irrigation systems, in computational pathology, battery development systems, etc. And I will finish with a simple case study. Let's first look at the application of these ideas in precision irrigation. The water-food energy nexus is central to sustainable development as demands for food, water, and energy are increasing, driven by population increases, driven by urbanization, changing diets, and economic growth. The world population, food and agriculture are the largest consumers of water, and almost 70% of the water we take from rivers and groundwater goes into agriculture use. The world population is already over 8 billion, and therefore we will need more food, water, and energy. Only 10% or less than 10% is used in domestic application, and 20% or less in industry. Also have to be aware that irrigated agriculture on average is at least twice as productive per unit of land. Irrigated food production therefore provides a buffer, an important buffer against increasing climate variability, and can ensure secure crop diversification and production. Many of these problems, when you look at agriculture systems, are at the confluence of soil physics, plant pathology, soil morphology, hydrology, meteorological sciences, image processing, and analysis. And more than 1/4 of the energy used globally is expended on food production, food supply, and transportation. I mentioned already 70% of the world's fresh water is used for agricultural processes. Here is an example of a commonly used irrigation system, the center point irrigation system. This is a satellite image of circular fields characteristic of the center point irrigation system in Kansas, covering hundreds of square miles, watered by the Ogallala Aquifer. The Ogallala Aquifer in Nebraska, Kansas, Wyoming, Texas continues to deplete at record rates. The pipe is on a pivot that rotates slowly around the field. Notice different crops in concentric circles. Irrigated agriculture will continue to play a key role in ensuring global food and production and nutrition security for a growing world population that is expected to increase to 10 billion by 2050. Be aware that aquifers are being depleted at record rates, and water tables are declining and also being contaminated with chemicals. Here is a satellite image of circular fields of the center point irrigation systems in the states of Kansas and Nebraska in the United States. The Ogallala aquifer continues to deplete at record rates. From wheat and cows to corn and cotton, the regional economy depends almost exclusively on agriculture irrigated by the Ogallala groundwater. Nutrient loading in wastewater agriculture remains the predominant source of nitrogen and phosphorus discharged into the environment. Agricultural intensification has already increased chemical use worldwide to approximately 2 million tons per year, with herbicides accounting for 47.5%, insecticides for 29.5%, fungicides for 17.5%, and others for 5.5%. Here is our vision for a smart irrigation system. The most important part is the field here, and the output of the field could be the yield, the crop yield, or it could be the moisture content in the field, or it could be the nutrient content in the crops that are to be harvested. The input is mainly the amount of water in the irrigation system. If we can measure different outputs such as the soil moisture, the nutrient loading in the crops, or the yields, we would therefore need sensing instruments. We feed these we would feed this data into a state and parameter estimation algorithm that depends on the agrohydrological model for the field and the crop. And we would be using Kalman filter algorithms for state and parameter estimation. Combine this with current and past weather information, geographical and crop data, and we would obtain estimated field data that we would feed into an advanced scheduling and control algorithm that would then decide on how much water irrigation should be used. We would also add to this current and predicted future weather conditions. Remember, if the future weather forecast says that it is going to rain tomorrow night or tomorrow morning, crops are generally very resilient and they can withstand several hours or days of no water. So you could use this as in a feed-forward control algorithm and give the right irrigation prescription for the deployment of the center point or any other root water irrigation system, and feed that into the plants. So we'd be using ensemble or unscented Kalman filters for estimating measurements such as the moisture content levels at various depths in the field. And for this you would need a good dynamic 3D agrohydrological model to track the evapotranspiration and the root water uptake by the plant. So the data that you need is weather forecast, satellite imagery data, agrohydrological models, and ensemble or unscented Kalman filter application. And the process that we would be dealing with would start from seeding to harvesting, and we would treat this as a batch process. Here is an example. Time to seed the plants, seed the field with seeds. The sprouts would turn up, and eventually the crops would mature and ready in a few months' time and ready for harvesting. All along the dynamics change, the roots go deeper in search for water in the soil. The color of the leaves and the foliage would change, and all of that would provide enough information for satellite imagery or drone systems to collect. So here is an example of drones being used to collect information on a field. For the center point irrigation system, we would use a specific representation that I outlined. We would use the polar coordinate system to understand the system, and this would tell us where in the grid to put our sensor. Many of these problems are at the confluence of soil physics, plant pathology, hydrology, soil morphology, meteorological sciences, image processing, and so on. Where should we be locating sensors on this grid? And can we infer soil moisture from satellite imagery or drones by flying them over agricultural fields? And here is an example of our estimated soil moisture content in a very large field in southern Alberta. This is the representation that we've used, the polar coordinate representation for fields which are being planted, which are being irrigated by the center point irrigation system. Here is another example of different representation. If you're looking for a sinusoid wave in terms of amplitude versus time, this is one way of analyzing this sinusoid. Alternately, you can do a Fourier transform and you would get a picture such as the following. This would give us the information on different frequencies that make up this sinusoid. We would have low frequencies, mid frequencies, and high frequencies. However, this FFT does not have the time localization. The time localization is missing in the spectrum plot. So the question to ask is, where did the low frequency sine wave or the mid frequency sine wave or the high frequency sine wave occur? For that information, it is better to look at a wavelet plot where the time as well as the frequency localization is preserved. So this plot tells us that the low frequency waves appeared in the first 125 samples, the high frequency waves occurred in the mid 125 samples, and then the mid frequency samples waves occurred in the last 125 samples. Next, we look at the application of machine learning algorithms for abnormality detection in image processing. And this is a step towards computational pathology. Let me explain this in more detail. Detecting and confirming the presence of malaria parasites in red blood cells is a highly error-prone process. In fact, many of the microbiology tasks in pathology are manual and highly error-prone. No two technicians would look at the same slide through a microscope and come up with the same number counts. So what is needed is consistency, and for this, deep learning methods on well-trained models can really achieve this consistency. And that's what I label as computational pathology. For this, for the diagnosis and subsequent confirmation of malaria, there are three important steps. We need to first detect the presence of a parasite. The presence of a parasite. followed by enumeration, meaning counting the number of parasites, the number of infected red blood cells, and finally speciation, which type of parasite has been detected. And for this, the algorithm that we developed consists of loading the image of a stained blood slide, pre-processing that because there are generally many artifacts in the image, obtain an RBC count, and then check for stained object detection and check if there are any stained pixels showing the parasite. If the answer is yes, we say that we've detected parasite, and then we have to go on to reload the image and obtain a parasite count. If there are no parasites, we conclude that that's an artifact. So here is an example. The circles are detected on binary image after removing spurious boundaries. We obtain a number count on the red blood cells, and depending on the size on the radii of the circles, we can even obtain a distribution of the RBC distribution, and this in fact can help. The distribution of RBC radii is also useful for other purposes, for identifying other diseases. Once we detect the parasites, we have to obtain the count of the parasites. In this example, we were able to show 4 red blood cells with parasites. Even though only 2 show up here, they appear on top of each other, and here we have 2 RBC cells with parasite. And finally, we have to obtain a count on the number of parasites, and for this we use the probabilistic k-means clustering algorithm to enumerate or obtain the number of parasites. And so in summary, a new method of image segmentation was proposed using probabilistic k-means clustering, and this handles the issue of unknown number of clusters, initial guess problem, retaining small clusters buried in large population by providing higher weights to small clusters, and so on. And finally, we were able to validate the execution of this algorithm versus manual count, and in almost all cases except for 2, we were able to get an accurate count. So this method can be used as a very good screening tool for identifying, detecting, and enumeration of malaria parasites. So such method can be applied to screen, detect, and diagnose many other diseases from stained slides via image processes. So these ideas can be applied widely in detecting other diseases as well from stained slides. What is needed is an extensive data set for each type of disease. And so what is required are images of stained slides for training purposes and the use of deep learning methods using convolution neural networks for detecting the abnormalities. Let's now look at battery technology. Batteries have transformed our lifestyle in the 20th century, and they promise to do even more so in the 21st century. Their development in the 1970s by Sony, the lithium-ion batteries have revolutionized everything from mobile phones to electric vehicles. And as the world looks to reach net zero emissions from vehicles by 2050, batteries need to become cheaper, have higher energy density, safer, they need to be safer, they need to be recyclable, and be made of ethically sourced materials. And therefore the need for safer and efficient mineral exploration and better batteries. Batteries research and development is a complex multivariate problem where very different properties such as performance, life cycle analysis, safety, cost, environmental effects, and resource issues are contained. And furthermore, the overall battery circular economy should eventually be included from mining, production, assembly, stage via long usage phase to the final reuse and recycling processes. What's driven the need for better batteries and looking for materials that make up the batteries is the exorbitant cost of materials that are currently used in conventional batteries, and that's cobalt and lithium. Look at the prices. In 2016, the average price was about $15,000 per ton, and now in 2022-2023, it's sitting at about $75,000 to $80,000 per ton. So reducing greenhouse gas emissions will require affordable batteries, and batteries need to become cheaper, have higher energy density, be safer, be recyclable, and be made of ethically sourced material. So this includes, among other things, replacing all fossil fuel-powered cars and trucks with electric vehicles. This will require manufacturing billions of electric vehicle batteries, and the need to discover and mine more mineable deposits of cobalt, copper, lithium, and nickel. How do we do this? Well, mineral exploration is now considered a data science problem. There is Eroom's law of mining. Eroom is Moore's law spelled backward, and this is known as Eroom's law. Moore's law is the observation that the number of transistors in an integrated circuit doubles about every 2 years, and to the date it has continued to be followed. Eroom's law of mining says that the number of ore deposits discovered per dollar of capital investment has been declining. It's the opposite of Moore's law. So here the number of ore deposits are declining by a factor of 8 over the past 30 years. So barely 1 out of 10 drill holes will yield an ore deposit. On the other hand, if you treat exploration as an information problem, combine geoscience expertise with data, and much of that information is available publicly. However, it is dispersed and highly fragmented. If you can collect all types of data, geophysical measurements, magnetic field measurements, seismic waves, satellite imagery in virtual and infrared bands, spectral reflection, induced electric currents, and so on, then it turns out the success rate is 8 out of 10. And here is an example. This is a shot of geologists looking for data in northern Quebec. And this article appeared in the 2023 June issue of IEEE Spectrum, where exploration is treated as an information problem. Combining geoscience expertise with data yielded almost a success rate of 8 out of 10 drill holes. So this is very recent. To reach net zero greenhouse gas emissions by 2050, we will need to combine AI and machine learning with geoscience expertise, but we will also need to have better battery technology. We will need to understand the electrochemistry, and use AI machine learning algorithms to accelerate the search for newer materials for battery electrodes, battery electrolytes, and explore different configuration of solid-state battery design. And the research workflow will rely heavily on forward trial and error approach and is largely materials centered. Involves synthesizing materials, manufacturing electrolytes and electrodes, assembling cells, and finally assessing the performance, leading to almost an infinite number of possibilities for choosing the right manufacturing parameters, and dozens of possible cell formats. This is far greater than what a human brain can handle. And so what is needed is deep understanding of material science and how the choice of electrodes and electrolytes will affect battery performance, and use this using ML algorithms. I want to finish up the identification of steel microstructure using machine learning method. What we did was we analyzed many different steel microstructures, and we fed this information, these images, into a deep learning neural net algorithm. And the goal was to identify steel structures which have low hardness, and low hardness can make dents in the material, identify steel structures with low toughness, which means that the material will crack and shatter, and identify steel microstructure that can be manufactured with the right composition, right carbon content, and the use of right cooling rate to yield better welds. We're using machine learning algorithms to find the specific metal structures that yield better yields. So we were feeding a lot of images into a deep learning, machine learning algorithm, and obtaining labeled micrographs that yielded better welds. You can quantify different microstructures in the weld heat zone, and thus identify process parameters that lead to good microstructures and better welding joints. AI has also been used to identify different tree makeup in a forest. And this is particularly useful in knowing which forests are perhaps prone to forest fires during the summer season because of lightning conditions. Last summer, Canada witnessed thousands and thousands of acres of forest fires because of tinder dry forest conditions, and that was ignited by lightning. So AI can be used to see the forest and the trees, and this article appeared in the August 2020 issue of IEEE Spectrum. Let me finish by showing a real-life example of developing a digital twin using very simple machine learning algorithm. The actual behavior of a process can be compared with the behavior predicted by a model. If the model is perfect and no abnormalities exist, then the error is white noise. Here is the error. And so instead of using process variables, the deviation of the error is monitored. So here is an example. This is data from a real industrial pump showing you the pump flow rate in gallons per minute and the pump head in pressure in PSI. And to a trained eye, it is impossible to detect the abnormality in this pump, but there is a serious abnormality, and we shall show how this can be detected. The domain information in analyzing this is important, and I've highlighted this, that in machine learning and AI algorithms, it is important to always capture the domain information. In this case, the domain information is about the pump specification. Pump specification, given the required head and flow rate, is always obtained from the pump characteristic curve as shown here. Depending on the desired head and flow rate, one can choose the right RPM of the pump. Well, it turns out these characteristic curves can be easily modeled using a simple second order polynomial as shown here, where H stands for the head, Q is the pump flow rate. So all we need to do is, from the pump data, identify 3 coefficients. And for this data set, we did exactly that. The green data is the pump data that I showed you earlier. The red curve is this curve, the second order polynomial, and we were able to identify the 3 coefficients. So using this as our pump model, we feed in the flow rate and we measure the actual head, and this, the model gives us the predicted head, and this, the error between H and the predicted head, is the prediction error. And I show you the plot of the prediction error. It is quite noisy because the flow rate data is always very noisy. And so even if you were to have a threshold such as the following, yes, you would identify the abnormality, but you would get quite a few false alarms. And in order to alleviate this, all we need to do is process the data. And we filtered this data using a 10th order moving average filter, which gave us this data, and now the threshold is able to identify the abnormality, and notice there are no false alarms. So you need to do some processing that I outlined earlier. No, we were able to detect the abnormality, and using this idea, one could have prevented the serious problem with the pump, which caused the entire plant to be shut down. We could have shut down the pump somewhere here, repaired the pump, and continued with the process. To finish up, what I want to say is data ingestion, data preparation, data pre-processing, bookkeeping, cleansing is an important preliminary step. Secondly, incorporating domain knowledge to formulate the analytics problem and the information extraction problem is important. Interdisciplinary teamwork will be required for projects to achieve success. And in the various examples that I have shared with you, you have to look broadly and in depth for successful applications of AI and machine learning algorithms. Overall, AI and machine learning techniques have the potential to revolutionize various industries, including the agriculture, battery development for energy storage, developing screening tools to identify diseases from stained slides, and classify metal microstructures that lead to better yields and joints. By leveraging the power of these technologies, manufacturers and engineers can optimize their processes and achieve higher levels of efficiency, productivity, and quality, leading to the design of more efficient, sustainable, and reliable systems. As all things digital continue to accelerate, which technology trends matter most for companies and executives? In the next decade, we will experience more progress than in the past 100 years, combined as technology reshapes health, material sciences, energy, and transportation, and a wide range of other industries. Look at industrial applications across a wide spectrum of industries, from power to food processing. Thank you for your attention.